Hi everyone, it's Tech Tuesday. This is Rick Yuzzi, and today I'm going to be talking about Wi-Fi 6. Stand by. Hey, this is Rick Yuzzi. Thanks for joining me again. This is Tech Tuesday. Welcome. So the topic for today is Wi-Fi 6, and I wanted to talk a little bit about kind of the basics of that. I'm not going to drill real deep, probably because I don't understand real deep. So this is going to be kind of a highlight or high-level discussion of what Wi-Fi 6 is. You may have heard of this coming out. A lot of people have heard about 5G. We talked about that in a recent broadcast. Wi-Fi 6 is the next generation of Wi-Fi that's coming out, and it's really something that's needed with the proliferation of devices that we have. Wi-Fi service has gotten a lot faster over the years, which is good, but it can be kind of limited in public areas as we have more and more people connecting with wireless devices. It's been an issue. We have more devices with Internet of Things that are connecting up, so there's a real need for Wi-Fi 6, and it's now been ratified with a standard. We can talk a little bit about this. So back a couple of months ago, the Wi-Fi Alliance did ratify the standard for Wi-Fi 6, and it's going to focus more on spectral efficiency. So while it's faster, a little bit faster than some of the other versions, speed isn't really what it's all about. It's all about spectral efficiency and being able to use the spectrum that we have between lots and lots of devices is what we're seeing, right? So that's the reason that this is needed. Now it is about 4 times faster than the last version, 802.11ac, which was a 5 gigahertz standard in a very congested area because of the way that it is so spectrally efficient. So we'll be discussing some of these things as well. This is the first time in the 802.11 Wi-Fi standard that the access point can coordinate communication with the clients. So this is a really big change. Before it was more kind of the Wild West and people were screaming at each other. Access points were listening to client devices that were all trying to communicate over each other. So this is going to be a big change with Wi-Fi 6. So now access points are going to be able to support a lot more clients, a lot more wireless clients, which is going to be good. There's going to be less congestion, but you can also have less equipment out in the area as well. This will be really good for buildings, for example, where you don't have to have access points all over the place, or in public venues like stadiums. It's going to be much, much better. There are already devices, even though it was ratified just recently, there are already devices out in the market because the standard has been developed over time. And sometimes the equipment manufacturer will get out ahead of the standard and try to start getting their equipment to market as soon as possible. So now that it is ratified, if they want this nice Wi-Fi 6 certified little banner, they're going to have to go back and make sure that everything that they put in their equipment that they've already got out on the market supports the standard, or maybe modify it so that it does. But it is out now. So what is it? Well, let's talk first about what we have as far as the different standards. So the 802.11 was the first standard, came out in 1997. 2.4 gigahertz was the band frequency, about 2 megabits per second. Again, the first Wi-Fi standard release. So in 1999, there were 2 updates to that, 802.11a and 802.11b. Now you probably never heard of 802.11a if you had a router back then, unless you maybe worked for a company where you were doing Wi-Fi kinds of things, because it was really more for commercial use. It used something called OFDM, which I'll explain here in a minute. And it could go faster, 54 megabits per second as opposed to 11 megabits per second, but the equipment was a lot more expensive. So for consumer use, people were using the 802.11b standard up to 11 megabits per second, so it was an improvement over 802.11. And then in 2003, 802.11g came out. That was on that 2.4 gigahertz band, 54 megabits per second again, and this added OFDM. And OFDM, again, I'll explain more in a minute, but that's orthogonal frequency division multiplexing that allowed more efficient use of the spectrum, and I'll explain that in a minute. 2009, 802.11 came out, 802.11n, 2.4 and 5 gigahertz, so it worked on both bands. You could use either 2.4 or 5 gigahertz, 300 to 450 megabits per second, and then that added something called MIMO OFDM. MIMO is multi-input or multiple input, multiple output. And that's where you started to see access points that had multiple antennas on them. And the reason for that was you could transmit to a single client, you could transmit over the air at the same time using 2 antennas, so you could send more information using 2 antennas. And the way it worked was because of the way Wi-Fi propagates in the air, it bounces off of various things, and if you send 2 signals out 2 different antennas, they're going to bounce off different things and arrive at the receiver maybe at a slightly different time from a slightly different direction, and that would be bad. That would be interference unless you're trying to control that. So with MIMO, they could control that and decode that. So now you could actually send basically 2 different streams to the same client, and it could interpret that when it got to it, and you could send more information that way. So that was MIMO. That was added 2009. In 2014, 802.11ac came out, 5 gigahertz only, 433 megabits per second up to 3.5 gigabits per second. So the speeds are getting pretty high here. That added beamforming. That's where you can take one of those antennas and you can actually really focus the direction that your beam is going as opposed to just broadcasting it all over the place. More streams, higher channel width on that. And then it added multi-user MIMO, or MU MIMO. And the difference there is, whereas MIMO was a single client, you could transfer multiple streams to a single client using multiple antennas. Multi-user MIMO, you can transmit multiple streams to multiple clients at the same time using multiple antennas. So that again increased efficiency of the spectrum and allowed you to talk to more devices at the same time. So that was a nice advantage there. So again, in 2019, just a couple months ago, they ratified the 802.11ax standard, and that's not a very sexy name, as you can tell. So the whole 802.11 thing, the Wi-Fi Alliance decided to call this Wi-Fi 6. As they did that, they've gone back and kind of renamed some of the older standards, Wi-Fi 5, Wi-Fi 4. I think some of the others are 3, 2, and 1. But those are kind of irrelevant at this point. So we've got Wi-Fi 6 out now, 2.4 gigahertz, 5 gigahertz, and up to 6 gigahertz now. And it's not called Wi-Fi 6 because there's the 6 gigahertz. That's just a coincidence. It's just the 6th generation is basically what they're saying of Wi-Fi. And this one, 1 gig to 10 gigabits per second. It added something called OFDM. That's orthogonal frequency division multiple access, and I'll explain more about that here in a minute. Something called target wake time, I'll explain that. BSS Coloring, I'll explain that. And then not just multi-user MIMO on the downlink, but also on the uplink as well. So MU MIMO was in 802.11ac was strictly down, and with Wi-Fi 6 it's going to be down and up, so that helps as well. So let's talk about some of these things. So first, OFDM, and I showed this slide when I was talking about DOCSIS 3.1 a while back with Peter Libby. We were going over what DOCSIS 3.1 was, and we were talking about OFDM, which is something that was added to DOCSIS 3.1. That's the standard for cable modem service. And OFDM has been around for a while. It's been around in the cellular world, and now then it came out in DOCSIS 3.1, and it's going to be, and it came out in Wi-Fi some time ago. And orthogonal means basically right angles. So what OFDM is doing is you've got a channel, and then that channel is divided into subcarriers. And with OFDM, you send down the signal at various times in such a way so that as that signal is going down the line and it's spaced in a certain way, that basically the signals don't interfere. So if you're looking at this picture, you've got these various signals, you have different subscribers, different client devices that you're transmitting to. And if you look at the dotted lines coming down, you can see that as that line comes down to that baseline right there, there's no interference with our signals because the peaks and the valleys are all canceling each other out. So you've got basically a null as that signal goes down the line. So OFDM is allowing you to have these different subcarriers and send lots of different signals down that line at the same time. And they don't overlap, which means they don't interfere. So that was OFDM. Now OFDM, and here's a good example of how it looks in the Wi-Fi world. So if you think about it this way, think about this channel. This is a 20 megahertz channel. Think about this being a highway. And before OFDM, this would be a one-lane highway, and you could have one car at a time going down that highway, and that's not very efficient, and it'd take you forever to get to work, right? So with OFDM, it's more like a 6-lane highway if you're looking at it this way. Let's say we've got 6 lanes, and you've got these 6 different clients, and over time you can transmit on this same OFDM channel. Again, through these subcarriers, you can, let's say, transmit to client 1, client 2, client 3, etc. And they all have their own lane, which is nice. And now let's say this is 6 and you can have 6 cars. So it's like a 6-lane highway. So you can be really much more efficient than before. But with OFDM, you can't have more than one car in a lane at a time. So that means you got to wait for that guy in lane 1 to get to work before you can ever get on the highway. So while it was more efficient than just not OFDM at all, it's not as efficient as OFDMA, which is orthogonal frequency division multiple access. And OFDMA uses the same kind of paradigm, but it uses something, in addition to these subcarriers, it breaks those subcarriers down into something called resource units, or RUs. Oh, sorry, that's an ROUS, which would be a rodent of unusual size, not an RUS. I always like to throw a movie reference in there, so that's for you Princess Bride fans. So resource units, if you look at this particular thing right here, this is similar where you've got these 6 lanes, let's say, but now you've got these, again, 6 clients, and you can break up these channels or these little time slices, and the access point can determine this. This is what determines this. It can then send, let's say, client 1 and client 2, it can send down that same lane at the same time, depending on how much data they need to transfer. So you can have 2 of these clients, or 2 of these cars, let's say, using that lane at the same time. In the next time slice, it's going to be client 1, 2, 3, and 4. So it's a smaller resource unit, but they can all use this little slice of this channel at the same time. On the third one, we've got client 5 is going to take up the whole channel. In that case, that's almost like the OFDM, but in this case, the access point determines that client 5 needs all of that. And again, you've got other examples here where you're sharing it equally again, or sharing the whole, client 1 using the whole channel. And then you've got another 6th one, we've got client 3, what is that, client 4, and client 6 all using this. And client 6 is getting a little bit more than the other 2. So the resource units are broken down that way. Here's another way to look at it. So in a 20 megahertz channel, you've got these subcarriers, and you've got really 256 of them. But because you need guard bands or guard subcarriers, you've got that reduces that a little bit. Then you've got pilot subcarriers that have to be in there. So you're really down to 242 of these subcarriers, which they call tones for some reason. So you've got these 242 tones that could make up one resource unit. Or again, you could share it among 2 client devices, and they'd have 106 tones each, or 2 resource units, or 4 at 52, or up to 9 at 26. So you can have up to 9 clients speaking on this one channel over these subcarriers at the same time. So that's what resource units are in OFDMA. Again, orthogonal multiplex division multiple access, something like that, I don't know. Target wake time. This is another thing that's very important for Wi-Fi 6 that's going to help with battery life as well as spectral efficiency. So what target wake time is, if normally in a Wi-Fi environment, you've got all of these clients out there and they're all online at the same time. So everybody needs to be awake and listening to see if they're hearing an access point that wants to talk to them, or if they want to talk to an access point, they need to be awake all the time. Well, what target wake time does, again, because with Wi-Fi 6, the access point can control what the clients are doing. It can negotiate with the client when it should wake up. So how often it needs to wake up, if it can sleep for a certain amount of time or go into a low power mode. And they have what they're showing in this diagram are some client devices. They're showing a phone and a tablet. And I don't know how relevant it would be for that kind of a situation, because your phone generally it wakes up when you want to do something, wanting it right then. I think it's probably more it's going to be more beneficial, obviously, in, let's say, the IoT or Internet of Things kind of area, where you've got lots of different monitors out there, lots of sensors and kinds of things that maybe don't need to be online and listening all the time. They just want to be able to report, maybe on a certain time frame, that every hour they're going to report some kind of data or something like that. So the access point can negotiate with all these devices out there, and if that device can be in a low power mode for a lot of the time, then you might have a device that is offline or in a low power mode most of the time, as opposed to being awake the whole time and using a lot of power. So obviously this is good for power use and battery use. It may help on mobile phones and things like that. There may be some ways that helps with battery life. So that's what target wake time is. And then there's something called BSS Coloring. And this will also help with battery life and contention, those kinds of things. In this case, they're showing the situation without this BSS coloring. And what the coloring is, it's not really a color, but again, the access point can negotiate with the client, and it can pick a little bit that it calls a BSS color. That's a basic service set color. And it would be a digit between 0 and 7, I believe. And it can help determine if there's going to be interference between those two clients. So it looks, they transmit this BSS color bit, and if they are hearing something on from another AP that's on a different color, then it can ignore that. It's kind of confusing, but if you're looking at I'll explain it better here in a minute, but if you're looking at this picture here, on the left side, you've got without this BSS coloring, and you've got this client device that's screaming, right? You see that kind of that blue circle around this phone, and it can be interacting with other access points and other clients in this particular Wi-Fi network. So with BSS coloring, the negotiation between the access point and the client device can be such that it can tell this client, hey, I hear you, you don't need to shout so loud, and we're going to be talking back and forth to each other on this tan color. And then if you're hearing this, if this client and this AP are hearing other colors like this pink color or this blue color, they're going to ignore that, because it's like these are not going to interfere with us. It's not loud enough to be a conflict. So that's the one way of looking at it. I think a better way of looking at it would be this. So if you're in a restaurant or a bar and you're talking at a table with some friends, and there's tables next to you and a table next to them, sometimes it's kind of hard to hear depending on how the environment and how loud people are talking. As one lady on the right here is talking to herself, which is kind of weird, but there's people like that out there that talk to themselves, and sometimes very loudly. So she could be like that access point or that client device out there that's just screaming, wanting to be heard. So if you've got these tables all next to each other, think of those as wireless devices, then let's say the table next to you, everybody's talking really loud, and you've got one guy who's talking really loud, you might not be able to hear the people around you. So you may have to go move to another room or another channel, let's say. So that's not a good thing. So because of the way Wi-Fi has worked in the past, all of these clients and access points are really trying to talk to each other real loudly so they can hear each other and hear each other over any interference that's around them. With this BSS coloring, again, there's this negotiation between the access point and the client, where first of all, it knows kind of which devices out there are most likely to interfere, and it can also negotiate with the clients that it's talking to and say, listen, I can hear you, you don't need to speak so loud. So now you can have a much better conversation with people around you and not have to have these other devices shouting. Again, you've got this person out on the end there who's talking to herself. Maybe she's not talking as loudly now, or maybe even if she is, she's far enough away from this table on the left that the access point knows that she's not going to be a bother. And the reason this is important is with the old Wi-Fi, I'm going to go back a slide here, with Wi-Fi prior to Wi-Fi 6, if any one of these people, you've got all these people sitting in this restaurant, if any one of these people, when they go to start saying something, hears somebody else, it doesn't matter if it's somebody talking low or somebody shouting out in the distance, if they hear somebody else, they can't speak yet. They got to wait for that person to stop talking. That's the way it works on Wi-Fi. If a Wi-Fi device in 802.11 AC, for example, or AN or any of these prior to Wi-Fi 6, if that device hears somebody else transmitting, it waits, and then it waits until nobody's transmitting, and then it transmits. So that would be analogous to these people not speaking until they hear nobody around them saying something. And it'd be like, can I get a word in? Can I get a word in? It'd be really hard to do. Obviously, it's faster with computers and Wi-Fi, but it's still, you can see how that would make Wi-Fi a lot slower, and it would make it a lot harder the more devices there are. Whereas again, with BSS coloring, now these people are speaking lower, and it's like you can ignore them. So I know, even though I can hear that lady down on the right there speaking, it's not loud enough where the friends around the table can, they can still hear me. So I don't worry about this little chatter that I'm hearing out in the distance. I can go ahead and talk. Now, if one of these people on this table next to me start talking really loud, in other words, maybe their access point is closer, and for some reason they're now interfering with me, then my access point, let's say, can then change me to another room. It can say, let me move you over to this table over here, it's more quiet. So these access points can make that change kind of dynamically based on what's going on. So you can see how this would, again, help. So you've got, I think, lower power requirements because you're not having to scream as loud. And you've got less contention. So you can have more devices in the same area using the same space, the airspace, so to speak, speaking to each other and not interfering. Now, another thing that's coming up with Wi-Fi 6 is 6 gigahertz. This is not yet, I don't think this is settled yet, because the 6 gigahertz spectrum, I believe, is licensed spectrum used by government and other things where they're trying to figure out now how this is going to be used. But you can see the benefits here with 2.4, 5, and 6 gigahertz spectrum. So you've got, on the 6 gigahertz, you've got much better throughput, obviously, than 2.4 and even 5 gigahertz. And a lot of that throughput has to do with the spectral efficiency more so than speed. There's better speed, but a lot of it's about how efficiently you can use the spectrum. And then range-wise, 2.4 gigahertz is actually the best in range, and then 5 gigahertz is much less, and then 6 gigahertz is a little bit less than 5. So, you know, this is an important point. If you're in your home now, you might be using either 2.4 or 5 or both. You might have devices on both, depending on your equipment. 2.4 goes a lot further, and that can be a good thing as far as coverage in your home, for example, but it can also be a bad thing. If you're in an apartment and your signal's leaking through to your neighbors, or even in a home, a lot of times, you know, you'll go to connect up your device and you look and you see your neighbors on each side, their Wi-Fi access points, and it may not be that strong, and it may be strong depending on what they have there, and maybe you could connect to it if you knew their password, or they didn't have a password. And there's a problem with that because your device is having to listen to that, even though you're not going to connect to that network. It's out there, and your device is going, oh, here's something out here that I need to listen to. So sometimes 5 gigahertz is better in a home, for example, if you've got enough coverage, because you don't need to worry about your signal going out as far. And then also the 5 gigahertz spectrum, there's less interference. On 2.4 gigahertz, you've got devices like baby monitors, you've got cordless phones, and other kinds of, a lot of IoT devices sometimes run 2.4, so you've got a lot more interference, other kind of devices that are going to be on there. 5 gigahertz is a little bit less interference because there's fewer devices on 5 gigahertz. And it also, because it doesn't go as far, you're going to be interfering less through different channels than 2.4. So you're going to be seeing less interference from devices that are near you because their signals aren't going as far. And then you've got the 6 gigahertz range. Again, the range is not that different from 5 gigahertz. And then on latency, this is a big one for 6 gigahertz. The latency on 2.4 is pretty high. It's much less on 5 gigahertz, and it's even much less on 6 gigahertz. And latency is important. That's the time that it takes that you're waiting for things. So latency on 6 gigahertz is going to be much, much better. So one of the things with 6 gigahertz, I mentioned, it's still not settled yet. And one of the reasons is they need to figure out, you know, on licensed spectrum, for example, if you're going to offer unlicensed spectrum, how do you keep people with unlicensed spectrum from interfering with each other? And especially maybe with somebody who's got licensed spectrum. And there was, they came up with something like this for the white spaces, TV white space, where you have a database, somebody maintains a database of all these people that are going to have these different spectrum that they're allocated. And they're talking about doing the same thing with 6 gigahertz Wi-Fi, where you will have to register with a AFC master, I think it is, and you'll register that you're going to be using the spectrum, and then based on everybody that's using the spectrum, you've got to ensure that your Wi-Fi is not going to interfere with other people's Wi-Fi. It's really complicated, and they're trying to figure all that out now, but I think they will. But the good news is that it sounds like they're not going to make this apply to in-home or in-building kinds of Wi-Fi, because, again, that's not going to propagate with the 6 gigahertz spectrum. That's not going to propagate very far when you're talking about inside a building, and it's not going to go that far out through the walls. So most likely you'll be able to have 6 gigahertz equipment, Wi-Fi equipment in your home or in businesses, and not have to worry about registering for outdoor kind of use. And with 5G, maybe there won't be that much outdoor use with Wi-Fi 6. We don't know. So again, just to kind of recap some of the benefits here with Wi-Fi 6, you've got reduced Wi-Fi congestion, which is mean less contention, faster throughput, more reliable because again, you're not having to contend with all of these other signals, and you're not having to wait. So again, as things get more congested and we get more and more devices out there, Internet of Things devices, more and more people on phones, it's going to be a much better experience. Imagine yourself in the stadium, with everybody else connected. It's going to be so much better handling this in very public places as well. Better battery life, especially for IoT devices, but maybe also for your phones, not having to transmit as loud, or maybe if there is some benefit, I don't know yet, some benefits with mobile devices in this target wake time. Again, the new 6 gigahertz spectrum will be opening up. You'll have lower latency and a better fit with 5G mobile service. So I talked about 5G in a previous broadcast and what that's doing for the cellular network. And one of the issues with 5G, if you're going to use what's called millimeter wave, which is really the exciting one because it's very fast and very low latency. If you're using millimeter wave, it doesn't go through walls. So 5G doesn't propagate very far. It doesn't go through, it's not good at going through trees and leaves and those kinds of things. It can't go around corners, so it needs line of sight. So you have lots of little antennas around on light poles and street lamps, those kinds of things. So you've got lots of antennas and you need a line of sight. So you can put, if you're in a more urban area and you've got 5G in your area and you've got a place where you can see an antenna, line of sight to an antenna, they can put a 5G antenna on your home. They may run it through the wall like you would a satellite kind of connection, or there's now, I believe Verizon has got something where they put on one side of the window, the receiver, and another antenna on the inside of the window, and then you can have the 5G make it into your home, although I don't think it's 5G. I think they're just transmitting the signal into the home. But really at that point, it's going to have to go to Wi-Fi because 5G, again, doesn't go through walls. So you've got this great, fast, low latency 5G internet service getting to your home, but not necessarily in your home. So if you're a gamer, for example, and you want low latency, that's not going to help you as much if you're on a 2.4 or a 5 gigahertz 802.11 N or AC or some kind of other Wi-Fi 4 or Wi-Fi 5 kind of service. So what Wi-Fi 6 does is it gives you lower latency and faster speeds within the home, and it can get through walls in your home. So I think that's going to be a better kind of fit for 5G. So that's another thing that will help in addition to just the overall benefits of Wi-Fi 6. So anyway, I hope this was helpful for you. If this video was helpful for you, go ahead and please subscribe to our channel. Just on the video right there, you should see a subscribe button. Go ahead and click that. And if you do subscribe, go ahead and ring the little bell to make sure that you get notified whenever we're live with a video or post a new recorded video. This video, again, if you like this video, if it was helpful, go ahead and click the thumbs up for me. I'd love to have some likes on that. So that's it for today's Tech Tuesday. We will be back next week with another topic. I haven't decided what that's going to be yet, so I'll be here, though, next Tuesday for Tech Tuesday. That's 3 o'clock, and we'll see you then.